Welcome to the Caterpillar Basics Library. Click the left-hand mouse button to select a course. Chapter 1, Diesel Engine Basics, explains combustion concepts, the four-stroke cycle, diesel engine components and how they operate. This introduction section explains the objectives and overall course structure of fundamentals of diesel engines. This course will help you understand basic operating principles of internal combustion four-stroke cycle diesel engines. Understand how the cooling, lubrication, charge air, fuel, and starting systems operate, and perform basic maintenance procedures on Caterpillar engines. Knowing how the engine works normally means you'll be able to recognize when the engine or engine system is not operating correctly. Diesel power. Power to move mountains. Power to move goods. Power to transform dry desert to lush farmland. Power to extract the raw materials used worldwide. Caterpillar diesel power has changed the way we do work. From ocean vessels and oil rigs to the trucks traveling the highways, diesels help get the job done. And you can help get the job done too. Whenever you service or repair an engine, a thorough and efficient repair keeps the machine out where it should be, working. The key to doing your job well is knowledge. Knowledge about the engine, how it works, how the systems operate under normal conditions. It all comes down to basics. Mastering the basics is what this course is all about. Fundamentals of diesel engines lays the groundwork, preparing you for advanced training on repair and maintenance procedures used on Caterpillar diesel engines. Diesel Engine Basics explains combustion concepts, the four-stroke cycle, and diesel engine components. The information in this chapter is the cornerstone for additional training on repair and maintenance procedures performed on a diesel engine. Diesel Engine Systems discusses the cooling system, its basic components, flow of fluids, and properties of coolant. The lubrication system, basic components, flow of fluids, and properties of oil. The air intake and exhaust system, basic components, and flow of air. And the fuel system, basic components, flow of fuel, injection principles, and properties of fuel. Your understanding of diesel engine systems and their normal operation is critical for future troubleshooting. Diesel Engine Systems Tests discusses tests you might have to perform during routine maintenance on the cooling system, lubrication system, air intake and exhaust system, and the fuel system. General maintenance procedures provides you with an understanding of how to gather information about the engine prior to performing maintenance. You'll learn how to determine a service interval, how to perform filter and fluid changes on the lubrication system and cooling system, how to perform filter changes on the fuel system and on the air system. And you'll learn how to take an SOS sample and read an SOS report. Maintenance procedures are critical to the life of the engine. Performing the procedures properly ensures long-running engines and satisfied customers. In this segment, you'll learn about the combustion process and how the combustion chamber and its components operate, how the engine uses reciprocating and rotary motion to transmit energy, and how combustion occurs during a four-stroke cycle. You will also be able to define top dead center, bottom dead center, and stroke. Think of an engine as a clock. Everything works in synchronization to keep good time. In a diesel engine, all the components work together to convert heat energy into mechanical energy. The heating of air and fuel together produces combustion, which creates the force required to run the engine. Air, which contains oxygen, is required to burn the fuel. Fuel produces the force. When atomized, diesel fuels ignite easily and burn efficiently. Combustion occurs when the air-fuel mixture heats up enough to ignite. It must burn quickly in a controlled fashion to produce the most heat energy. Air plus fuel plus heat equals combustion. Combustion is controlled by three factors: the volume of air compressed, the type of fuel used, and the amount of fuel mixed with the air. The combustion chamber is formed by 1. The cylinder liner, 2. The piston, 3. The intake valves, 4. The exhaust valves, and 5. The cylinder head. When air is compressed, it heats up. The more you compress air, the hotter it gets. If it's compressed enough, it produces temperatures above the fuel's ignition temperature. The amount of fuel is also important because more fuel produces more force. When injected into an enclosed area containing sufficient air, a small amount of fuel produces large amounts of heat and force. More fuel equals more force. The type of fuel used in the engine affects combustion because different fuels burn at different temperatures, and some burn more thoroughly. In a diesel engine, air is compressed inside the combustion chamber until it's hot enough to ignite the fuel. Then fuel is injected into the hot chamber and combustion occurs. In a gasoline engine, compressed air does not provide enough heat for combustion to begin. A spark plug ignites the mixture which creates combustion. In both engine types, combustion produces heat energy, which causes the gases trapped in the combustion chamber to expand, pushing the piston down. As the piston moves down, it moves other mechanical components that do the work. The components work together to transform reciprocating motion into rotary motion. When combustion occurs, it moves the piston and connecting rod in an up and down motion called reciprocating motion. The connecting rod turns the crankshaft, which converts the reciprocating motion into circular motion called rotary motion. This is how the engine transforms the heat of combustion into usable energy. The cycle starts with the intake stroke. First, the intake valve opens. At the same time, the piston moves to bottom dead center, or BDC, its lowest point, pulling air into the combustion chamber. The crankshaft turns 180 degrees, or half a revolution. The exhaust valve remains closed. During the second, or compression stroke, the intake valve closes, sealing the combustion chamber. The piston moves up to its highest point in the cylinder liner, called top dead center, or TDC. The trapped air is compressed and very hot. The amount the air is compressed is called the compression ratio. Most diesel engines have a compression ratio between 13:1 and 20:1. The crankshaft has turned 360 degrees, or one complete revolution. The formula for compression ratio is bottom dead center volume divided by top dead center volume. Diesel fuel is injected near the end of the compression stroke. This creates combustion and starts the power stroke. The intake and exhaust valves remain closed to seal the combustion chamber. The force of combustion pushes the piston down, which causes the connecting rod to turn the crankshaft another 180 degrees. The crankshaft has now made 1.5 revolutions since the cycle started. The exhaust stroke is the final stroke in the cycle. During the exhaust stroke, the exhaust valve opens as the piston moves up, forcing the burned gases out of the cylinder. At TDC, the exhaust valve closes, the intake valve opens, and the cycle begins again. The connecting rod had turned the crankshaft another 180 degrees. At the end of the exhaust stroke, the entire process is complete. During this time, the crankshaft has completed 2 360-degree rotations. Taken together, the intake, compression, power, and exhaust strokes are called a cycle, thus the name the four-stroke cycle. Cat engines use the four-stroke cycle, and the cycle occurs over and over as long as the engine is running. The sequence in which each cylinder comes to the power stroke is called the firing order of the engine. 4 strokes of piston equals 2 revolutions of crankshaft. In this segment, you'll learn the differences between diesel and gasoline engines. Like diesel engines, gasoline engines use combustion from the four-stroke cycle to create energy to do work. But there are some slight differences in the process. Let's see what those differences are. Probably the most obvious difference between diesel and gasoline engines is that diesel engines do not require a spark for ignition. Instead, air is compressed to such a high ratio that it heats the air in the combustion chamber enough to ignite the fuel. Combustion chamber design is also different between diesel and gasoline engines. In diesels, there's very little room between the cylinder head and the piston at top dead center, producing the high compression ratio. Most diesel pistons have the combustion chamber formed right into the top of the piston. In gasoline engines, the combustion chamber is formed into the cylinder head. The space between the piston and cylinder head is larger than in a diesel, resulting in a lower compression ratio. Another major difference is the amount of work the engine is capable of performing at lower RPM. In general, diesel engines usually operate between 800 and 2200 RPM and provide more torque and more power to do work. Both engines convert heat energy to motion using the four-stroke cycle. Diesel engines are generally more fuel efficient for the amount of work output than gasoline engines. It requires relatively small amounts of fuel to produce the rated horsepower output in a diesel engine. Diesel engines are generally heavier than gasoline engines because the diesel engine must withstand higher combustion pressures and temperatures. Diesel engines generally use higher compression ratios to heat the air to combustion temperatures. Most diesel engines generally have a 13:1 to 20:1 compression ratio. Gasoline engines generally use compression ratios between 8:1 to 11:1. In this segment, you'll learn how a spark-ignited engine operates. Spark-ignited engines run on gaseous fuels like propane, methane, and ethanol. These fuels and the requirements for low-pressure fuel lines required significant modifications of the engine design. Since World War II, Caterpillar has marketed a limited number of gas engines. Today, Caterpillar produces gas engines for the irrigation, industrial, cogeneration, and generator set markets. In recent years, the United States and other countries have instituted strict emissions guidelines to protect and preserve the environment. Natural gas has emerged as an environmentally clean and abundant fuel. To meet the changing market, Caterpillar has made the commitment to supply gas engines throughout its product line. These engines run on gaseous fuels like propane and methane. Based on Cat diesel engine design, many gas engine parts are the same, but significant modifications have been made primarily in the fuel delivery system. The air intake, exhaust, cooling, and fuel systems have been changed to accommodate leaner air-fuel mixtures, and a high-voltage spark ignition system has been added. On some engines, the piston has also been redesigned with a deep cup to facilitate combustion. On others, a flat-top piston is available. Electronic sensors and timing devices have been added to improve engine performance on these low-emission engines. Gas engines are currently available from the 3300, 3400, 3500, and 3600 families. Currently, gas engines are used to compress and transport gas in natural gas fields, run irrigation pumps, and power cogeneration plants. In this segment, you'll learn the common terminology used to describe how an engine functions and how well the engine operates. Engines are described using many terms and phrases. Some describe how an engine functions, while others describe how well the engine operates. There are three main categories of terminology in this topic: laws of mechanics, power output, and engine efficiency. Laws of mechanics terms describe the motion of objects and the effects of motion. Friction is the resistance to motion between two surfaces in contact with each other. For example, friction exists between the piston and cylinder wall as the piston moves up and down. Friction produces heat, which is one of the biggest contributors to wear and component damage. Inertia is the tendency of an object at rest to stay at rest, or an object in motion to stay in motion. The engine uses force to overcome inertia. Force is a push or pull that starts, stops, or changes the motion of an object. Force is created by combustion during the power stroke. The higher the generated force, the more power is produced. Pressure is a measure of the force exerted per unit area. During the four-stroke cycle, a lot of pressure is produced on the top of the piston during the compression and power strokes. There are three ways to create pressure: increase temperature, decrease volume, or restrict flow. Many systems and components of internal combustion engines operate under or generate specific pressures. Knowledge and measurement of specific pressures throughout the engine can provide a great deal of information about the overall engine health. Engine power is described according to the quality and quantity of certain characteristics. Torque is a turning or twisting force. A crankshaft exerts torque to force flywheels, torque converters, or other mechanical devices to turn. Torque is also a measure of the load-carrying capacity of the engine. To compute torque in foot-pounds, multiply 5,252 by the engine's horsepower, then divide by RPM. Torque rise is an increase in torque that occurs when an engine is lugged down from rated RPM. This increase in torque occurs until a certain RPM is reached, after which torque drops rapidly. The maximum torque level reached is called peak torque. The formula for torque rise is peak torque minus rated torque multiplied by 100, then divided by rated torque. Horsepower is a rating given to the engine that describes the amount of work output over a period of time or the rate of doing work. Brake horsepower is the usable power available for work at the flywheel. Brake horsepower is less than true horsepower because some energy is used to move the engine components. The formula for horsepower is RPM multiplied by torque and divided by 5,252. Heat is a form of energy produced by the combustion of fuel. heat energy is converted into mechanical energy by the piston and other engine components in order to produce power suitable for work. Temperature is a measurement of relative warmth or coolness of an object. It is usually measured with either a Fahrenheit or Celsius scale. The British Thermal Unit, or BTU, is used to measure the heat value of a specific amount of fuel, or the amount of heat transferred from one object to another. A BTU is the amount of heat required to raise 1 pound of water, 1 degree Fahrenheit. BTU is used to describe a fuel's heating value. Fuels with higher BTU ratings generate more heat and therefore more power. In general, diesel fuel has a higher BTU rating than gasoline. BTU is also used to describe how well the cooling system works. The more BTUs the coolant removes, the more efficient the cooling system. Engine design affects engine performance and efficiency. Bore is the interior diameter of the cylinder measured in inches or millimeters. The bore of the cylinder determines the volume of air available for combustion. With all other things being equal, the larger the bore, the more powerful the engine. Stroke is the name for the distance the piston travels from top dead center to bottom dead center. Stroke length is determined by the design of the crankshaft. A longer stroke allows more air into the cylinder, which allows more fuel to be burned, creating more power. To compute displacement, multiply bore area by stroke. To compute compression ratio, divide total volume, when the piston is at bottom dead center, by the compression volume, when the piston is at top dead center. After completing this topic, you will be able to identify the components in the block, cylinder head, and gear train assemblies, and understand the function of each component. In this segment, you will learn about each component in the block assembly and be able to describe the function of each component. The block assembly is where the power is created. Let's look at each of the block assembly components and how they work together to make the engine operate. The engine block is the structure that supports all the components for the engine. The cylinders are holes in the engine block that perform a number of tasks. They house the pistons, they form the combustion chambers, and they move heat away from the pistons. Pistons perform 3 primary jobs. They transmit force of combustion to the connecting rod and crankshaft. They seal the combustion chamber, and they transmit excess heat away from the combustion chamber. Each piston has 2 or more rings that fit into grooves on the piston. They have 3 primary jobs. They seal the combustion chamber. They control lubrication of the cylinder walls. And they cool the piston by transferring heat generated by combustion. Connecting rods are attached to every piston via the piston pin. The connecting rod transmits combustion force from the piston to the crankshaft. The other end of the connecting rod turns the crankshaft located at the bottom of the engine block. The crankshaft transmits rotary motion to the flywheel, providing energy suitable for work. The camshaft is driven by a gear on the crankshaft. The camshaft controls the valve opening and closing, and may control fuel injection when unit injectors are used. The camshaft gets its name from the egg-shaped lobes or cams. As the camshaft rotates, the lobes turn. Valve train components linked to the camshaft follow the motion, moving up and down. When the nose of the lobe faces up, the valve is all the way open. The flywheel assembly is the link between the engine and the load. It is bolted to the rear of the crankshaft. A flywheel performs three jobs. It stores energy for momentum between power strokes. It smooths out the speed of the crankshaft. And it transmits power. Push rods are steel tubes with seats on both ends. The camshaft moves the push rod, causing it to lift the rocker arms. A valve lifter or cam follower rests on each cam lobe. As the camshaft turns, the lifter moves, following the shape of the lobe. Engine blocks come in different designs. Inline engines have the cylinders all in one row. V engines separate the cylinders into two rows, and the block has a V shape. Blocks are normally gray cast iron. Coolant and lubricant passages are cast into the block. Cylinders can either be cast permanently into the block, called a parent bore, shown in example 1, or they may be removable cylinder liners. Cylinder liners form the water jacket wall between the coolant and pistons. Wet liners have O-rings to seal the water jacket and prevent coolant leakage. Dry liners are often used to repair or sleeve parent bore engines should a cylinder fail. The liners are called dry because they fit against pre-existing cylinder bore walls in the block. A cylinder liner is made of cast iron. A typical wet cylinder liner has several parts. The inside surface, number 1, is heat-treated and finely honed with a crosshatch pattern. It holds the piston and is also called the cylinder bore. The fire dam, 2, seals the combustion chamber and protects the head gasket. Number 3 is the flange. It supports the liner in the block. The filler band groove, 4, holds a filler band, which helps the liner fit into the bore and reduces liner vibration. The outside surface, 5, forms the water jacket wall inside the block. And 6, the O-ring grooves hold O-rings, which seal the water jacket. A piston fits inside each cylinder liner and moves up and down during combustion. The top of the piston forms the bottom of the combustion chamber. The piston, which transmits the force of combustion, is made up of many parts. The crown, number 1, contains the combustion chamber. The ring grooves and lands, number 2, hold the compression and oil control rings. 3. The wrist pin bore contains a pin that connects the piston to the connecting rod. The retaining ring, 4, keeps the piston pin inside the pin bore. And 5. The thrust skirt carries side loads. Number 1 shows an undercrown area on the inside of the piston. Some pistons contain oil cooling galleries inside the piston crown, which cannot be seen, shown here as number 2. Pistons are constructed using a variety of methods. Some have a cast aluminum crown and a forged aluminum skirt, which have been electron beam welded. Some are composite pistons, which means a steel crown and forged aluminum skirt are bolted together. And articulated pistons have two pieces, a forged steel crown with pin bores and bushings, and a separate cast aluminum skirt. The two pieces are held together by the wrist pin. The most common type is the single-piece cast aluminum piston with an iron band that carries the piston rings. There are two styles of pistons which relate to fuel system and combustion chamber design. Pre-combustion pistons, like the one on the right, have a heat plug in the crown. Direct injection pistons do not have a heat plug. There are two types of piston rings, compression rings and oil control rings. Compression rings seal the bottom of the combustion chamber by preventing combustion gases from leaking out past the pistons. There is usually one oil control ring below the compression rings. Oil control rings lubricate the walls of the cylinder liner as the piston moves up and down. The oil film reduces wear on the cylinder liner and piston. Behind the oil control ring is an expander spring which helps maintain an even film of oil on the cylinder wall. All rings have a hard facing to increase ring life. Every piston ring has a gap between the two ends of the ring. To prevent leakage, ring end gaps should not line up when installed. Connecting rods link the piston to the crankshaft. There are several parts to all connecting rods. Number 1 is the rod eye. 2 is the piston pin bushing. 3, the shank. 4, the cap. 5 are the rod bolts and nuts. And 6 are the connecting rod bearings. The rod eye holds the piston pin bushing. The piston pin bushing is inside the rod eye. Bushings are a type of bearing which distribute load and can be replaced when worn. The shank extends the length of the connecting rod. It has an I-beam shape for strength and rigidity. The crankshaft bore and cap are at the large end of the connecting rod. They surround the crankshaft's rod bearing journal and attach the connecting rod to the crankshaft. The rod bolt and nuts secure the rod and cap to the crankshaft. This is called the crank end or big end of the connecting rod. The connecting rod bearings are in the crank end of the connecting rod. The crankshaft turns inside the connecting rod bearings, which carry the load. The connecting rod bearing's top half fits in the rod and is called the upper half shell. The other half fits in the cap and is called the lower half shell. Generally, the upper half shell carries more load. The crankshaft transfers the piston's reciprocal motion into a rotary motion that is used in performing work. There are many parts to the crankshaft, including number 1, the rod bearing journals, 2, the counterweights, 3, the main bearing journals, and 4, the webs. Crankshafts for inline engines generally have only one rod bearing journal for each cylinder, while V engines share a single rod bearing journal between two cylinders. The rod bearing journals determine the position of the pistons. When the journals are up, the pistons are at top dead center. When the journals are down, the pistons are at bottom dead center. The firing order of the engine determines when each rod bearing journal comes to top dead center. Some rod bearing journals have lightening holes to reduce the weight of the crankshaft and to help balance the crankshaft. The crankshaft has drilled oil holes to get oil from the main bearings to the connecting rod bearings. Drilled oil passages are plugged at one end by a cup plug or set screw. Main bearing journals and rod bearing journals are held together by webs, shown here as number 3. The radius between the web and the journal is called a fillet. Some webs have counterweights to help balance the crankshaft. These counterweights may be part of the crankshaft forging, or in some cases they are bolted on. Crankshafts use main bearings to support the crankshaft in the block. Main bearings are in line with each other. This is a thrust main. It's one of the main bearing journals. Its web has wide ground sidewalls. It works with the thrust main bearing to limit crankshaft back and forth movement, called end play. The crankshaft turns inside main bearings that are tightly clamped in bores located at the bottom of the block. Crankshafts for inline engines generally have only one rod-bearing journal for each cylinder, while V engines share a single rod-bearing journal between two cylinders. The main bearing assemblies consist of the main bearing bores in the engine block, the main bearing caps, which are held on with bolts or studs, and the main bearings themselves. The upper halves of main bearings have an oil hole and usually a slot, so lubricating oil is continuously fed into the oil hole in the main journal. Thrust main bearings minimize back and forth movement of the crankshaft. There are two types of thrust main bearings. Insert bearings are two pieces. Flanged thrust bearings are one piece. The thrust main works together with a thrust bearing to minimize back and forth movement of the crankshaft within the block. This movement is called end play. The flywheel assembly consists of 1, the flywheel, 2, the ring gear, and 3, the flywheel housing. The flywheel is bolted to the rear of the crankshaft in the flywheel housing. The crankshaft turns the flywheel on the power stroke, and the flywheel's momentum keeps the crankshaft turning smoothly during the intake, compression, and exhaust strokes. The ring gear, which is located around the flywheel, is used for starting the engine. The flywheel performs 3 functions. It stores energy for momentum between power strokes, smooths out the speed of the crankshaft, and transmits power to a machine, torque converter, or other load. On the front of the crankshaft, you may find a vibration damper. Dampers control torsional or twisting vibrations of the crankshaft. A damper resembles a miniature flywheel that's either pressed on or bolted to the front of the crankshaft. Vibration dampers are available in 2 basic designs, a rubber damper and a viscous damper. A rubber vibration damper shown on the left uses dense rubber to absorb the vibrations. A viscous damper on the right uses heavy oil to absorb the vibrations. The camshaft is driven by a gear on the crankshaft. As the camshaft rotates, the cam lobes turn. Valve train components linked to the camshaft follow the motion, moving up and down. When the nose of the lobe faces up, the valve is all the way open. The camshaft turns at half the speed of the crankshaft so that the valves open and close at the correct time during the 4-stroke cycle. The purpose of the camshaft is to control intake and exhaust valve operation. All camshafts have bearing journals, shown as number 1, and lobes, number 2. Separate lobes operate the intake and exhaust valves for each cylinder. Some cams have fuel injection lobes, shown here as number 3, which operate unit injectors. These control when fuel is injected into the cylinder. Every lobe is made up of 3 main parts. 1, the base circle, 2, the ramps, and 3, the nose. The distance from the base circle diameter to the top of the nose is called lift. Cam lift determines how far valves are opened. The shape of the opening and closing ramps determine how fast the valves open and close. The shape of the nose determines how long the valve is fully opened. Number 1 is for fast valve opening. 2 would provide a long open period. 3, a fast close. And 4, a slow close. The camshaft journals turn in the camshaft bearings. Camshaft bearings are press-fit into bores in the engine block. They contain an oil hole that aligns with an oil passage in the block. A valve lifter or cam follower rests on each lobe of the camshaft. As the camshaft turns, shown here as number 1, the valve lifter follows the shape of the lobe. The valve lifter transmits the motion of the camshaft to the pushrod. The push rod transmits that motion to the rocker arm to open and close the valve. There are two types of valve lifters, slipper followers and roller followers. Roller followers have a hardened steel roller that rolls on the camshaft lobe. Roller followers slide up and down in bores in the engine block and are kept aligned by special clips. Slipper followers are usually one-piece castings with a wear face that contacts the lobe. The slipper followers slide up and down in bores in the engine block. Slipper followers rotate slowly while the engine is operating. Some components which are most susceptible to wear are designed to be replaced. These include cylinder liners, piston rings, main bearings, and connecting rod bearings. Because of the extreme temperatures and pressures generated by combustion, cylinder liners become worn by pistons and rings and are designed to be replaced. Because of high combustion temperatures and constant motion, piston rings will eventually wear and are designed to be replaced as needed. Main bearings will wear faster than the crankshaft because they're made of softer metal. Therefore, bearings are designed to be replaced when necessary. Connecting rod bearings will wear faster than the crankshaft because they're made of softer metal. Therefore, bearings are designed to be replaced when necessary. In this segment, you will learn about cylinder head components and the function of each component. You will also learn how an overhead cam engine operates and how its valve train differs from a pushrod engine. The cylinder head and its components are designed to make sure that the valves open and close and that fuel is injected at the proper time for peak engine performance. The valve train assembly includes, number 1, the cylinder head, 2, the valve cover, 3, the bridges, 4, the valve spring assemblies, 5, the valve guides, 6, the valve seat inserts, 7, the valves, and 8, the rocker arms. The cylinder head is a separate casting which seals the top of the engine block and holds the valves, injector, or pre-combustion chamber in place. It also houses the valve train, some fuel system components, and water passages for cooling the parts. The cylinder head, number 1, is seated to the engine block with gaskets, 2, a spacer plate, 3, and bolts or studs. Depending on the engine design, the cylinder head can either be a single casting that covers the top of the block or several castings that cover one or more cylinders each. You must remove the valve covers in order to reach the valve train components. Rocker arms link the valves to the camshaft and changes the rotary motion of the camshaft to the reciprocating motion in the valves. As the push rod in the block pushes up on one end of the rocker arm, it pivots on the rocker arm shaft and pushes down on the valve mechanism, causing the valve to open. As the camshaft continues turning, the push rod lowers and the force of the valve spring closes the valve. There is a separate rocker arm for intake and exhaust valves on every cylinder. A rocker arm consists of 1, an adjusting screw to adjust valve lash, 2, a lock nut, which locks the screw in place to maintain lash, 3, a wear seat, which is a hardened insert to prevent rocker arm wear, and 4, a rocker shaft bushing, which provides a bearing between the rocker arm and the shaft. The rocker arm pivots on a shaft that's usually fastened to the cylinder head. When the cam lobe starts to move the push rod upwards, there's usually a little gap or clearance between the rocker arm and valve bridge that assures the valve is able to close completely. This is called valve lash and is one of the more critical adjustments that must be made on the valve train. Bridges are used if a cylinder has multiple intake and exhaust valves. On these engines, The bridge assembly transmits rocker arm motion to all intake or exhaust valves on a cylinder simultaneously. Components of the bridge include 1. A wear seat to reduce bridge wear. 2. An adjusting screw which compensates for differences in the height of the valve stems. 3. A lock nut which sets the adjusting screw. And 4. A bore which rides on a guide pin. Bridges fit on bridge dowels. Bridge dowels fit into bores in the cylinder head. The valves control flow of air and exhaust gases through the combustion chamber. When the intake valve is open, air is allowed into the combustion chamber. When the exhaust valve is open, exhaust exits the combustion chamber. Each valve consists of 1. The keeper grooves, where keepers grip the valve stem to hold the spring on. 2. The valve stem, which extends the length of the valve. 3. The valve fillet, which joins the head of the valve to the stem. 4. The valve seat, a hard facing which reduces wear and seals the combustion chamber. And 5. The valve face, which is the flat portion of the valve. To completely seal the combustion chamber, every valve has a valve seat insert located in the cylinder head. When the valve closes, the valve seat contacts the valve seat insert. On most engines, the valve seat inserts are replaceable. Valves move up and down inside valve guides, which are mounted in the cylinder head. Valve guides keep the valves traveling in a straight line. The valve stem extends out of the guide on top of the cylinder head. Valve springs keep the valves closed. Valve springs fit over the valves and are held in place by a combination of keepers, number 1, and 2, either a retainer or rotator. Retainers or rotators fit over the end of the valve stem. Retainers lock the keepers into the grooves in the valve and provide a seat for the valve spring to press against. Valve rotators turn the valve to prevent excessive wear in one spot. The valves, valve seat inserts, and valve guides experience the most wear because of the high combustion temperatures and pressures. All are replaceable components. Fuel nozzles or unit injectors are also located in the head. The nozzles fit between the valves. Fuel nozzles are held in place with a sleeve, washers, adapters, and keepers. Different engine models use different valve train designs. These include 1. A pushrod engine, 2. An overhead cam engine, and 3. A cam-in-head engine. Engines which use a camshaft, valve lifter, pushrod, and rocker arm are referred to as pushrod engines. Overhead cam engines have a camshaft, shown here as number 1, in the cylinder head. Valve lifters, number 2, are linked to the top of the valve stem. As the cam lobe rotates, the lifter follows the motion and opens the valve. As the cam continues to rotate, valve spring force closes the valve. Overhead cam engines do not require pushrods. In a cam-in-head engine, the camshaft is located in the cylinder head. Rocker arms ride on the lobes. As the camshaft turns, the rockers push the valves open. In this segment, you will learn about the components in the gear train and the function of each component. The gear train assembly is a series of gears that transfer power from the crankshaft to other major components in the engine. Gear trains may be located on the front and back of the engine. The gear train shown here is located on the front of the engine between the backing plate and timing gear housing. The gear train synchronizes all the components in the engine, so they work together during each stroke of the combustion cycle.
Here are the components of a typical gear train. Number 1, the crankshaft gear. Number 2, the idler gear. 3, the camshaft gear. 4, fuel injection pump gear. 5, oil pump gear. 6, the water pump gear. And 7, the air compressor gear. Timing marks are used to align the gears and help ensure proper timing. The crankshaft gear is mounted on the crankshaft. As the crankshaft turns, the gear turns as well. All other components are timed and driven by the crankshaft and crankshaft gear. The idler gear keeps the camshaft gear turning the same direction as the crankshaft gear. The gear ratios ensure that the camshaft turns at 1/2 the speed of the crankshaft. The camshaft gear meshes with the idler gear. It turns at 1/2 the speed of the crankshaft to make sure the intake and exhaust valves open and close on the correct stroke. The fuel pump gear is driven by the camshaft gear. Since they are the same size, they both turn at the same speed. The fuel pump gear turns the fuel pump camshaft, which works with the fuel system components to deliver fuel to the engine at the proper time. Some engine models use balance shafts. The shafts are driven from the crankshaft. In this example, there's a balance shaft on each side of the engine. The balance shaft eliminates excess vibration of the crankshaft. This is an example of a balance shaft and gear assembly. The oil pump gear is driven by the crankshaft gear. The oil pump circulates oil throughout the engine. The water pump is driven by the water pump gear and circulates coolant throughout the engine. The water pump gear is usually driven at the same speed as the crankshaft. Some engines use an air compressor to supply air to brakes and other components. The air compressor is driven from gears in the gear train. The air compressor gear meshes with idler gears and turns at the speed recommended by the manufacturer. A pulley assembly attached to the crankshaft drives other components like fans or alternators. All the timing gears are protected by the timing gear housing. The timing gear housing seals the front of the engine block.